What is the three-compartment model when we're talking about pharmacokinetics? This is an attempt to model how drugs behave in the body by simplifying the body's tissues into three separate compartments that handle the drug differently. And we start with our central compartment, which is our blood. We can put drug into the blood by injecting it intravenously, and drug is removed from the blood by the kidneys or liver or however it's metabolized and eliminated. And each of these processes have a rate constant determining how quickly that occurs. Now, if you just give a bolus injection really quickly, then this rate constant is pretty irrelevant. But let's say you're giving it as an infusion, then there will be a infusion rate, and the rate constant is K from 0 to 1. So from outside the body into the first or the central compartment. And then the elimination constant is the rate of elimination from 1 outside the body. So that's K10. But we don't just have the blood to think about, we've got other organs and other tissues, and we divide these into two further compartments, depending on how much blood supply they get. We have compartment 2, which gets a lot of blood supply. These are your brain, liver, kidneys, organs that receive a lot of blood very quickly. And we also have compartment 3. These are things like your muscle and fat, and they get less blood supply than the other organs. Now, to get into either of these compartments, the drug has to be injected into the blood, and then it has to be distributed by the blood to those organs, and then it has to diffuse across into that organ or that tissue. And that's why we separate it into those that have a high blood flow and those that have a low blood flow, is because their drug is going to be preferentially distributed to the high blood flow areas and less is going to get to the low blood flow areas. And each of these processes have their own rate constant as well. So this would be K from 1 to 2, and this would be K from 1 to 3. And we can imagine that drug is going to go more quickly into our brain, our liver, our kidneys than it is going to into our muscle and fat, by virtue of the fact these get more blood supply. Now, once we've got some drug in compartment 2 and compartment 3, then some drug is going to diffuse back into the blood. And these also have their rate constants. So this would be K2 to 1, and this would be K3 to 1. So to summarize quickly, we can put drug into the blood and we can take drug out of the blood. But to get into our high blood supply areas and our low blood supply areas, it has to come from the blood first. So we say that these and these are redistribution components, because we're not injecting more drug to get it into compartment 2. It is simply redistributing from the blood in and out of compartment 2. Likewise, it's redistributing from compartment 3. So we have two redistribution phases and we have an elimination phase. So if we think about this, we're going to give, let's for example take propofol. We're going to inject propofol into the blood and it's going to redistribute into the brain where it gets our clinical effect, but it's also going to distribute into fat and muscle, and then we're going to stop giving the propofol and it's going to be eliminated from the blood. But as it's eliminated from the blood, the concentration in the blood is going to drop. So the gradient is going to reverse. There's going to be more in here than there is in the blood and more in here than there is in the blood. So then you're going to get drug drifting back across down its new concentration gradient. And what that's going to do is top up the concentration in the blood, which means the plasma concentration is going to drop as drug is eliminated, but it's going to drop more slowly if you've got a big reservoir of drug in your other compartments that is still diffusing back in and topping that blood concentration up. And that is why the graph of drug concentration over time looks like this. This graph is a 3-phase exponential decline, which means over time, the rate at which the plasma concentration, we're using the log of the concentration here just to make the graph a bit smaller and easier to use, but essentially your plasma concentration, once you've stopped giving the drug, is going to drop over time as the drug is eliminated from the body. But your plasma concentration is gradually going to reduce at a slower and slower rate. That's why the gradient is getting less and less steep, because this elimination constant will eliminate the same proportion of drug in any given time period, which means it takes the same amount of time to go from this value to half of that value as it does to a quarter and so on. This is what we call a half-life. It takes the same amount of time to drop by the same proportion. That's what exponential negative declines in pharmacokinetics generally refer to. but it's not just a single smooth graph, it's got three distinct phases. And this first phase is the redistribution phase. You've injected the drug into your central compartment, and it is very rapidly redistributing, and the plasma concentration drops. This drop in plasma concentration is not because the drug is being removed from the body, it is because it is moving from the plasma into other areas of the body. Then we move into our second phase. Now this is when we start to see drug being removed from the plasma, and so the concentration in the plasma is dropping. Now this process is slower than the redistribution, but it's after the redistribution has finished, and these levels and the concentration in these compartments are now fairly equal. The redistribution slows down because they are at equilibrium. We then get into this second phase where we are now starting to remove drug from the vascular space. So we have a slower removal. Once we get to a point where the plasma concentration has dropped to the point where it is lower than the concentration in these two compartments, you will start to get drug diffusing back into that central compartment and topping up the concentration while it is being removed. And that is why this final gradient is even shallower, because even though drug is being removed from the plasma at the same rate, at the same time you're getting more drug coming back in from the other compartments, and that's why it takes much longer for that plasma concentration to drop. That is why in the 3-compartment model, the graph of plasma concentration over time drops in a tri-exponential decline.